Hello, today we're continuing with our series of GCSE physics revision looking at the universe. For our purposes, the universe is essentially defining absolutely everything that there is. The universe contains billions of galaxies. Each galaxy contains billions of stars. Our Sun is one star, and that star is in a galaxy called the Milky Way. Milky Way is a spiral galaxy, which means stars sort of shoot off from the centre as if in a spiral arm, and we essentially are here. We are some way along, we're out from the centre, we're some way along from the centre on one of the arms of the galaxy. And the nearest star to us is a distance of 40 times 10 to the 12 kilometres away. And between us and that star, apart from, of course, the local planets which go around our Sun and a bit of space debris, but by and large, between us and the next star is absolutely nothing at all. Now, if this is the distance between us and the next star, you can see that universal distances are massive, 10 to the 12 kilometres. We need another unit which is easier to use. And the unit that we use is called a light year. And it's quite simple. A light year is actually a measure of distance, not, as it may seem, a measure of time. A light year is the distance which light travels in 1 year. So how much is that? Well, we know that light travels at 3 times 10 to the 8 metres per second. So if we want to know how far light travels in 1 year, we take the distance that it travels in 1 second, which is 3 times 10 to the 8 metres. We multiply that by 60 seconds, that gives us the distance in minutes. The distance it travels in 1 minute. We multiply by 60 again, that gives us the distance it travels in 1 hour. We multiply by 24, that gives us the distance it travels in 1 day. And we multiply by 365, and that gives us the distance it travels in 1 year. And that is 9.46 times 10 to the 12 kilometres. And on that basis, as you'll see, if the nearest star is 40 times 10 to the 12 kilometres, then the nearest star is approximately 4.2 light years away. And that's a much more manageable number. So it's 4.2 times the distance that light travels in 1 year. So now let's try and get an understanding of the range of the universe. We'll start by thinking about the distance between the Earth and the Moon, which is approximately 3 times 10 to the 8th metres. It's not quite, but for an approximation that will do. That, of course, is the distance that light travels in 1 second. So we can call that 1 light second. We normally use light years, but this will do. It's the distance light travels in 1 second. What is the distance between the Earth and the Sun? Well, that is, as I've said, 150 million kilometres, which is 1.5 times 10 to the 11 metres. And it takes light about 8 minutes to travel from the Sun to the Earth. So we could call that 8 light minutes. What about the width or the diameter of the whole of the solar system? So if you travelled from the extreme edge of the solar system right the way across to the Sun in the middle and then to the other side, that would be 4 times 10 to the 12 metres, which is about 20 times the distance from Earth to the Sun. So that's about 160 light minutes, or if you like, nearly 3 light hours. So it would take light approximately 3 hours to travel from one side of the solar system to the other. Then what's the distance between the Earth and the nearest star? Well, I've already told you that. It's 4 times 10 to the 12, sorry, 4 times 10 to the 16 metres. And we worked out what that was. That was 4.2 light years. So you can see now something of the extent of that distance. To travel across the solar system would take light just less than 3 hours. To travel between the Earth and the nearest star would take light 4.2 years. So you now get an idea of just how much space there is just between us and the nearest star. So how far is it from us to the nearest galaxy? Well, that is 2 times 10 to the 22 meters. Or, wait for it, 2 million light years. So if you want to travel to the next galaxy, even light would take 2 million years to get there. And if you ask, what is the distance across a galaxy, like the Milky Way or the next galaxy, which is called Andromeda, very approximately, that's 10 times 10 to the 21 meters, which is approximately 100,000 light years. So it takes light 100,000 years just to go from one side of the galaxy to another side of the galaxy. But it takes 2 million years to travel from one galaxy to another. So once again, you can see that there's a huge amount of space between galaxies that essentially has nothing in it. And so we come to the final question then, what is the distance across the universe? And I suppose I have to answer and say, nobody knows, because there's only a seeable universe, and there may be a lot more universe before it that we can't see. But a rough estimate of what one might be called the observable universe is 10 to the 27 meters. And that is a staggering 100 billion light years. In other words, it would take light 100 billion years to cross the universe. So you get some idea of the scale of the universe. And so finally, I want to deal with something which is called the Fermi Paradox. This is after a man by the name of Fermi. And essentially, the argument that Fermi put forward is this. We are saying that the Big Bang happened 13.7 billion years ago. We are also claiming that the Sun was formed, our very own Sun, 5 billion years ago. And it's got another 5 billion years to go, but that's about okay. And we're saying that the Earth on which we live was formed about 4 billion years ago. So essentially, from the beginnings of the Earth until now, 4 billion years have gone by. So life has formed during the course of that 4 billion years. Now, says Fermi, since the universe itself has been around for 13.7 billion years, there was presumably a Sun Mark II, a different star, in other words, that formed, let's say, 6 billion years ago. In other words, it's 1 billion years older than our Sun. And there must be a planet orbiting that star, which we could call Earth Mark II. After all, there are billions and billions and billions of stars. Surely, says Fermi, one of them will have a planet rather like the Earth, Earth Mark II. And that was formed, of course, about 5 billion years ago. In other words, it's 1 billion years older than us. So, surely, says Fermi, a civilization, life, and ultimately a civilization formed on that Earth. And that civilization will be 1 billion years ahead of us. So they surely will have cracked all the big problems. They have solved all the medical problems. They'll have worked out how to travel very large distances. They'll have worked out how to communicate. And therefore they will have travelled, at least they will have communicated with other civilizations, and they may even have travelled to other civilizations. And yet, we have absolutely no evidence of any civilization out there in the universe. Yet you'd have thought that if there were a civilization that was 1 billion years ahead of us, think of how much you would expect to discover in another billion years. If there are civilizations, and Fermi says there mustn't only just be one, there might be thousands of civilizations out there, surely one of them would at the very least have communicated with us in a way that we could recognize. And yet we've seen absolutely nothing, which led Fermi to ask the question, where is everybody? The Fermi Paradox. If there are billions and billions of stars, then there must be billions and billions of planets, and at least some of them would have the same conditions as our Earth to enable life to form. And many of them would have formed long before our Earth was formed. So the civilizations on those planets are much older than ours. They will have learnt more, they will have cracked more of the problems. They ought to have learnt how to do space travel. They ought to have learned how to communicate over vast distances, but we don't detect it. Where is everybody?